Thanks for coming. Glad to be here. Today, I'm gonna give an update on the Cosmo initiative, how we build open world models to help physical AI developers. But first, let's review the evolution of AI. So we started with generative AI, and now we are roughly in the agentic AI era. Next, gonna be physical AI. In generative AI, the key milestone are chatbots like a ChatGPT, content creator like a Nano Banana, and we were able to build those powerful AI models because we have tons of internet data. Over the past few decades, people have populated knowledge, image, visual content in the internet. They are valuable to train those state-of-the-art Gen AI models. Agentic AI is about digital tool use. And I think the milestone we have been experiencing today is coding model like Cloud Code, Codex has changed how software programming works. And we also have this OpenClaw to help you make a reservation, answer emails, configure your computers. So a while ago, when you hit issues, when compiling some libraries or install something, you probably go to a website called Stack Overflow to post your question, and there could be experts to help you come up with the answers. And those information become valuable starting point to train those agentic AI models. And now, with the coding agent become better, you can actually use them to simulate output, interact with your digital tool use. As long as the result is verifiable, then you can quickly generate huge amounts of training data. So I believe agentic AI will be also very successful because we have a way to create large-scale digital tool use data. Right? Gen AI is successful because of a huge amount of large-scale data, and agentic AI gonna be successful because we have a way to create huge amount of digital tool use data. Physical AI is about Gen AI to control physical tools, from digital tools in agentic AI to physical tools. And popular physical tools, including vehicles, robots, humanoids. So for humanoids, we have these chicken egg problems. We don't have humanoid robots surrounding us to collect huge amounts of training data. And because we don't have huge amounts of training data, we couldn't build a powerful humanoid models. And because they are not powerful, people are not buying that. So we need to have a way to break this deadlock, to find an initial set of training data to get those robots good enough to start this physical AI revolution. So my talk today and the mission of Cosmo is about how to create large-scale physical AI data to turbocharge physical AI developers. This is how we look at the physical AI data problem. We have a pyramid. The bottom is internet scale data. Those data are not from robot perspective. It's mostly from information sharing or storytelling perspective. But they encode the dynamic of the world, how things happen in the real world, in the physical world. We can build a world model, like NVIDIA Cosmos, to capture the knowledge in this internet scale data. A world model can understand and simulate the physical world. And with this world model, we can start to generate synthetic data more tailored to robot perspective. You can also leverage physics engine like NVIDIA Newton to help you create training data for training world models that are difficult to capture in real world or to supplement some synthetic data. But with these two, are not sufficient. You still need some in-robot data. In-robot data capture the correspondence between observation observed by the robot and the action taken by the robot to connect observation to action. And with these three, the in-robot data, synthetic data, and world model, you can start to build physical AI agents. And though some of them are passive data, they are not react the action of the physical agent during the training time. But a world model is interactive. And we build Cosmos for that. And before going further, I would like to play this famous video clip from The Matrix, 1999.
How was he? 10 hours straight. He's a machine. I know Kung Fu. Show me.
So what we want to do in Cosmo ultimately is build the matrix for robots, not for human, for robots. So that robot can learn all sorts of skills interacting with the world model before we release to the real world. It wouldn't damage your surroundings because you had gone through all the training in computing in simulation. So ultimate Cosmo, I think it's gonna be a generative training facility for physical AI. It's a training facility. The input is an agent, environment, and task. The output is the agent. The output agent is a beta agent with the skill to complete the task in the environment. So let's start with these simple examples. Right? The input can be a robot policy, and there's a target environment, can be a kitchen. The task is pick up knife and cut cucumber into sizes. Initially, the policy, the input agent, doesn't really know how to do that. But through this generative training facility, we'll be send the agent to many kitchens, to the kitchen and with the tool to do the task. And after some training, come out with an agent that can do this. Right? An updated robot policy with the skill to pick up a knife and cut cucumber into sizes in that kitchen. And if you are coming from a machine learning background, you know that one way to make a model more powerful is augmentation. We can start with environment augmentation. Instead of that kitchen, we can have K kitchens. When K becomes large, then the updated policy is gonna be able to do in many kitchens, even unseen kitchen, generalized. And you can also augment the task. You can augment environment and task simultaneously, and through the generative training facility, the updated policy, the output policy will be a stronger one with many skills. They can operate for many kitchens. And many skills even cover unseen skills. Okay. And to build this generative training facility, the world model, the ultimate Cosmo need to have two fundamental capabilities. The first one is the understanding and reasoning capability, so that it can look whether the agent complete the task in simulation. Right? Look at the final state and check out the task. What is the task and the final state to see if the agent really complete the task. And based on that, you have a reward R, and the reward used to update your policy. You also need to have this prediction or generation capability to simulate the future. The agent, the policy in that environment, based on the current state and the task, and predict the action to take. And based on the action, the world model reacts and gives a new state, and operates sequentially, eventually see if it's really complete the task. So from here, I want to say that these both understanding and prediction capabilities are fundamental to build a generative training facility, the ultimate Cosmos. And we are not yet there. Still a long way to go. But what I want to say is, as we march toward the final goal, the intermediate result created through this journey are already useful for the physical AI developers of today. The understanding capability can be a great video analytic tool to help you make sense of what happened in your observation, your sensor signals. Generation capability can help you create synthetic data. Combining understanding and prediction capability can help you with policy evaluation to evaluate the quality of policy model before, in the virtual world instead of deploying the real world. And if this model has great understanding and generation capability, it can be a good starting point for your policy model. You can train a policy model, fine-tune a policy model from these great starting points. So Cosmo today, before we achieve the ultimate goal, it had consists of the following components to help the physical AI developers. So it has models, scripts, framework, and blueprints. We currently have 3 different models. Reason, Cosmo Reason, in the 2nd generation. Predict, also 2nd generation. Transfer. Reason is for understanding. Predict and transfer is for generation. We have scripts for inference and for post-training. We also have a Cosmo cookbook to help you figure out how to use the models. We have framework, Cosmo Curator, to help curate physical AI data to post-train the Cosmo model. We have a framework, Cosmo IO, to do IO post-training on top of Cosmo models. We also have Cosmo Evaluator to evaluate the quality of the post-trained Cosmo models. We have blueprints, which are examples connecting Cosmo models to digital tools for production workflows. We have this something called VSS blueprints, visual search and summarization. We'll talk about it later. And also have Cosmo Data Search and Physical AI Data Factory. And our current Cosmo model ranked #1 for world generation for physical AI, for the benchmark of physical AI bench for the open source one. And also ranked #1 for open visual language model for physical AI understanding. And so far, since released last year, we have 6 million plus downloads. I want to say that we built Cosmo model to be a great backbone for many physical AI developers. During the day of conception of Cosmo, we believe that post-training is going to be a critical part of Cosmo because every robot sees the world differently. Some cars have 7 cameras, some have 12 cameras, some have LiDAR sensor. Humanoid robots are all very different. We believe that we should provide post-training scripts and help physical AI developers pre-train a backbone Cosmo models so that the post-trained model can be more tailored to their embodiments. And we are developing Cosmo to achieve this goal. Okay, now let's dive into 3 of the Cosmo models: Cosmo Reason 2, Cosmo Predict 2.5, and Cosmo Transfer 2.5. Okay, Reason 2. Cosmo Reason 2 is a physical understanding model. It takes a video input and prompt, and through a vision language model architecture, and generate output. It will do the thinking before generate the output. And Cosmo Reason 2, we just released in CS this year. We currently have a 2B version and 8B version out there, and the 32B version and 235B version coming soon. All the checkpoints are available in Hugging Face, also with the post-training script. So it's currently ranked #1 on Open Visual Language Model benchmark in 2 benchmark datasets. It can be used to analyze what happened in the video. The first one to see if there's a potential danger in the power grid. The second one to make sense of what happened in the driving video. And this has been the backbone model to help some of the physical AI developments internally at NVIDIA. You may have heard about the NVIDIA Alpha Mayo effort to build a driving policy model, and also NVIDIA's goods effort to build a policy model for humanoid. Cosmo is the backbone to support these two internal efforts. So we are dogfooding our own backbone model and try to make sure it's useful to the physical developers. And here, let's talk about Cosmo Predict. It's a video prediction model given a current frame and the text prompt, it predict the future. It supports multiple prediction mode. It can a single image input or multiple image video as an input. And we currently have two models, Cosmo Predict 2.52b and 14b model. We support diffuser and also a post-training script. It's gonna be available as a NIM on a couple of CSP. So with the pre-trained predict model with post-trained script, you can post-train it to achieve better performance in your target domains. You can also make it multi-view, like what you would observe from a robot, a head camera plus 2 gripper cameras. And it can also be a backbone for your policy model. And here, I'm gonna talk about play this Cosmo policy.
Cosmos policy, fine-tuning video models for visual motor control and planning. Open source video generation models like NVIDIA's Cosmos can generate diverse robot videos given input images and text. Can we post-train these models to also generate actions that control a robot? In this work, we introduce Cosmos policy, a robot policy fine-tuned from the NVIDIA Cosmos Predict 2 video model. We post-train Cosmos to predict not only future images, but also robot actions and values. There are two modes of deployment for Cosmos policy. A, just deploying the policy by itself, or B, deploying the policy with model-based planning using the future state and value predictions. Cosmos policy deployed just as a normal policy without any planning achieves state-of-the-art performance in the Libero simulation benchmark with a 98.5% average success rate. Cosmos policy also achieves state-of-the-art performance in the RoboCasa simulation benchmark, outperforming prior methods with significantly less training data. Here we show the actual images observed during rollouts in the top row and the futures that Cosmos policy predicts in the bottom row. The future image predictions are not needed outside of model-based planning, but they can provide useful visualizations of the policy's intent. Now, how well does Cosmos policy work in the real world? Let's see it in action. Here we see that Cosmos policy can perform language-conditioned pick and place following the user's prompt. Here, Cosmos policy performs a long-horizon, contact-rich manipulation task, folding a t-shirt with many steps with only 15 training demonstrations. Here, Cosmos policy performs consecutive object placements, handling a training dataset with high-action multimodality given random alternations of left arm versus right arm usage. Here, Cosmos policy operates with high precision and carefully grasps and opens a Ziploc bag before putting a candy inside, a seemingly simple task that is more challenging than it looks. Overall, in our real robot evaluations, Cosmos policy shows strong performance, even outperforming recent vision language action models such as Pio5 and OpenVLA OFT. Going further, once the policy evaluations are complete, the recorded rollouts can be used to further refine Cosmos policy's world model and value function. Then, Cosmos policy can better plan action trajectories with higher likelihood of success through model-based planning. For example, we show how Cosmos policy can do best of n search with n equals 3 samples for illustration. First, the current state is fed as input into Cosmos policy, which generates n candidate action chunks. Then, Cosmos policy's world model predicts the resulting future states, and its value function predicts the future states' values. The highest value action chunk is selected and deployed on the robot, and the search is repeated for the next action chunk. It is also possible to extend the search tree by auto-regressively rolling out the world model and querying the policy on the predicted futures through multiple layers. We can get the value prediction in the last layer, use that to select the highest value branch, and deploy the first action chunk in the branch. Let's see how model-based planning can help on challenging test cases where the base policy has trouble. Here, the base Cosmos policy struggles to grasp the candies and ultimately places just 1 of 5 candies into the bowl. However, with model-based planning, Cosmos policy makes greater progress and fetches 4 out of the 5 candies. In another task, we see that the base Cosmos policy sometimes fails to maintain its grasp of the Ziploc bag while opening it. However, we find that planning can help avoid common failure modes like this. The planning policy avoids the mistake and continues on to successfully complete the task. Here we show the futures that the world model predicts during a rollout after we refine the world model using policy rollouts. We observe that the actual futures tend to follow the predicted futures throughout the episode. Now we show examples of future state and value predictions seen during model-based planning. Given the current state, Cosmos policy generates n candidate futures. For simplicity, we just show 2 candidates with a search depth equal to 3. The value function assigns higher value to the future on the right, since it shows better progress towards opening the Ziploc bag. Let's see another example. Here, the futures are more semantically similar, but the value function prefers the more confident prediction on the right. In general, the differences between predicted futures can be subtle, but these subtleties can compound and affect the episode's outcome, even if they're not obvious to the human eye. Fortunately, a learned value function provides a data-driven way to search through even subtle differences to achieve a better outcome. Overall, we find that model-based planning improves Cosmos policy's completion score by 12.5 points on average across challenging settings. To see how Cosmos policy works and learn more about it, please visit our website. Thank you.
So I particularly like this work because I think it's connected to the model-based approach where you can predict the future states and predict their value and take the best outcome. It's like a data strategy with you in your physical AI agent. Another application of the Cosmo predict model is it can be used for policy evaluation. You can post-train Cosmo predict so that it conditions on the action taken by the robot. Right? So now each action taken by robot changes the state, the states observed. Right? And so with this, you can do the policy evaluation by just burning compute. Right? So you have let's say if you train any policy model, you might have 100 checkpoints. How do you know which one is the best? You're gonna deploy all 100 checkpoints in your physical AI robots. It might not be efficient, right? So with this action conditional model, the video model, you can connect your policy to this model. So every action taken changes the state, and you look at the final state to see if it complete the task. Okay, if the ranking with this model, this action condition video model, is same as what you would observe in the real world, then it becomes a proxy to help you develop faster. And we conduct some experiments, test out whether it's true, and we found that there's a positive correlation. So a policy performs better in real world, in the virtual world, with the world model, also it's a better policy for the real world. The last model in this family is Cosmo transfer. So it's a model that can convert control input into photorealistic video outputs. And the current Cosmo transfer model supports the following control signal: depth, edges, segmentation, or blur the inputs. They can be used individually or together in any combinations. And this becomes the control signal to change how the Cosmo transfer convert the noise to the video. And it can be used for multi-view or convert physics engine rendering output to become more photorealistic. And you can also use the style image to change the look of real video footage to help you create variations. And we conduct a set of experiments to verify whether Cosmo transfer help you build a better policy. And there's a baseline, and there's a base model, the policy model, trained just purely on demonstration. And there's a baseline augmented with the synthetic videos, and you use Cosmo transfer to create more variation. And we found that use Cosmo transfer, it gives you a policy that's achieved higher success rate. And with this multi-view capability, it helps you to build a driving simulator. Here, you can have a world scenario. It's more like a semantic representation of what you observe in the street. Right? You have bounding boxes like moving vehicles, lines like landmarks, and this is the semantic input. And you can use Cosmo transfer to convert to what you observe in your car, the multi-view videos. We actually use it to build a driving simulator. It's available in one of the demo booths this year called Alpha Dream. It's a real-time generative closed-loop autonomous vehicle simulator. So we connect it to a steering wheel. So now when you turn left, turn right, you will see the video react to your turning action. And we can have a user to control the steering wheel, or have a driving policy like a Alpha Mayo 1 to control the steering wheel. With the driving policy, we can do this closed-loop simulation to help improve the model. So the action generated by Alpha Mayo 1 go into this Alpha Sim to create the world scenario map, the bounding boxes and landmarks I showed you earlier. And those be converted to a real video input through Cosmo transfer. And those real video input is now observed by the driving policy and to make the next action. And the Alpha Mayo 1 is built on Cosmos reasoning capability, and this Alpha Dream is built on Cosmos generation capability. We had a busy year. So Cosmos was announced 2025 in January. At that time, we released two kind of video model. One is called Cosmo 1 diffusion-based video model. Then the other is a Cosmo AR, autoregressive-based video model. We also released the tokenizers. And in March, we released Cosmo Transfer 1, the first transfer version, and Cosmo Reason 1, the first understanding version of Cosmos. And in June, we released Cosmo Predict 2, a better version, a better diffusion-based backbone for generation. And in October, we have an update on the Predict 2.5. We also have Transfer 2.5. This January, we released Cosmo Reason 2, and we also released Cosmo Policy. And they are announcing that we are now doing the Cosmo 3 early access. And I want to say that earlier we built the understanding capability and generation capability in two different models. In Cosmo 3, we're gonna bring all of them together. So it's gonna be a single model that can do understanding and generation. And it's gonna be an Omni model, and it take input including image, video, sound, text, and action. And the output also have text, when you do reasoning, and for generation, you have image, video, sound, and action. So this model itself can be an action conditioned video generator, but it also can predict action. We use the mutual transformer architecture. So there are two main transformers in the backbone. One is for reasoning. We call it reasoner. The other is called Generative. They are tight coupled together so that it's a single model. Here I'm gonna talk about some applications. Since release Cosmo has been used by many people, and this is one application apply Cosmo to healthcare. So we can convert semantic segmentation of surgical videos into realistic one. You can, as a way to create training data, surgical transfer, powered by Cosmo transfer. And we can also directly generate challenge surgical operation video through this transfer, predict. And like what we built for the driving policy, we can also build a surgical simulator to interact with the policy model. And we have a blueprint for video search and summarization. So you can see that you might have a factory, there are so many cameras. How do you identify all the critical events, whether the workers are following the safety protocols? We can use the understanding capability built in Cosmo to help you to do it in scale. It can be many live camera streams, and we can ask the VSS to see whether there are events need your attention. So we also build this physical data factory blueprint to help you generate physical data. So you can leverage both physics engine or leverage the data that you have and use transfer to create augmentation and use the reason to help you describe the videos and to provide rich annotation to the video data for your applications. And so in this GTC, we also announced GROOT N1.7. It's the latest iteration of our humanoid policy model. So GROOT N1 built on top of Cosmo reasoning capability and it's optimized for the humanoid robots. And we have a set of tools provide you to help you customize this model to better tailor for your use case. Cosmo Cookbook is a great place if you want to see what you can do with Cosmos. We have many recipes to get you a quick start to get the hands-on on the Cosmo models. So, okay, let's back to the beginning. We built Cosmo, try to solve the physical data problem. And what the approach we are taking is to trade the compute for data, right? So it's difficult to collect those physical data in real world, but if we can generate them to help you accelerate your physical development. And of course, when you have more compute, you can generate more data. And I also want to take this opportunity to explain world models, right? So there are two kinds of world models. One is for the digital world, the other is for the physical world. The digital one, the world is what the digital agent experience. It can be your computer, it can be a compiler, a software environment. And of course, you can build a world model for that. But what we are focusing in Cosmo is for the physical world. The real physics and how physical AI agents interact with the real world. And in this physical world, you have understanding and generation. Both are important. Understanding help you make sense out of the world, and you can understand, can reason the potential outcome. And generation help you simulate the future. And we build Cosmo as a great backbone to help physical AI developers. And we started by supporting our internal physical AI developers, including our autonomous driving team and our robotics team. I want to take an opportunity to talk about tomorrow. I'm gonna we're gonna have this panel discussion, and there are gonna be 4 great panelists: Professor Stephen Norman from Stanford, CTO of Runway, head of Firefly Research from Adobe, and the CEO of Black Forest. And we're gonna talk about diffusions and what next. And so I want to also advertise our VP of Research, Sanya Fiedler, gonna have a session on advancing autonomous vehicle with world models. And there are also a follow-up session on, talk with the Cosmo experts in this GTC event. And I guess I will conclude my talk here. And thank you.